What if I told you your fridge, that humming box in the kitchen, could be cooled without gas, without chemicals, just magnets? It sounds futuristic, but researchers are already making it happen. It not only promises higher efficiency, but solves a critical problem with the status quo. Yes, a critical problem that even my beloved heat pumps have. The thing is, we need an alternative to refrigerants. Caloric cooling is one alternative, and one U.S. research team claims that magnetocalorics in particular are already on their way to replacing our current coolants with systems that are much more attractive. But how do you control the temperature with a solid material rather than a refrigerant gas? What makes magnetocalorics stand out? And is this cooling tech solid enough to redefine what it means to be a fridge magnet? Welcome to Think Tech today. This video is about how magnetic cooling is breaking all the rules. Magnetocalorics may not be mainstream, but they're not moving at a glacial pace. A few new commercial products have already hit the market that cool with magnets. One German company is already selling a beverage cooler and offering pre-orders for a 2-door commercial refrigerator. At the end of last year, you could grab yourself a drink out of a functioning fridge displayed by a French-German company at a heating and cooling technology trade fair. Shortly after that, a major update came from the Ames National Laboratory in the U.S. that kicked off our investigation into this topic. This is our second dive into the world of caloric cooling, so if you caught our earlier video on elasticalorics, some of this might ring a bell. But I promise, there's a very big material difference here. Instead of stretching the limits of refrigeration tech, today we'll talk about how researchers have been throwing magnets at the wall to see what sticks. The vapor compression cycle behind our freezers and HVAC systems is centuries old. At its core, it's all about phase changes. Nature's clever trick that lets 5 billion heat pumps, fridges, and ACs shuffle heat around to keep us comfortable. But as elegant as that system is, it relies heavily on refrigerants, mostly hydrofluorocarbons or HFCs, that change phase throughout the cycle. And as you probably know, HFCs come with some serious environmental baggage. It's clear our approach to climate control could use an upgrade, and swapping refrigerants for magnets might be just the retooling we need. To understand the greater study of caloric cooling, we first have to understand what we're working with. If you weren't around for our first exploration into caloric effects, or maybe your memory has just vaporized, here's a compressed refresher. Our current generation of cooling units, whether it's a window AC or an old-school icebox, are all heat exchangers. A heat exchanger is just a machine that moves heat from a hotter place to a cooler one. Most cooling devices rely on 4 main components: a compressor, condenser, expander, and evaporator. These make up the vapor compression cycle, which breaks down into 4 key steps. 1. First up, the compressor. It boosts the temperature and pressure of the refrigerant vapor. 2. Then, the condenser kicks in, turning that vapor into a liquid and releasing heat in the process. 3. Next, the expander drops the pressure of the refrigerant. As it expands, it cools down, colder than the space we want to chill. 4. Finally, the evaporator absorbs heat from the surrounding area, vaporizing the refrigerant. And just like that, the cycle repeats, with the compressor grabbing that warm vapor and starting all over again. Now you can confidently explain how your fridge works. Perfect the next time you need a cool icebreaker. But this method is everywhere. Given that vapor compression dates back to the 19th century, it's fair to say our refrigerators have been running strong for a long time. So, how could magnets possibly catch up and improve on that? Now that we've handled the data overload, let's get back to the thermal overload. Magnetocalorics, or magnetic cooling, have been an ongoing field of study for researchers interested in dumping refrigerants. Or maybe no longer having to worry about the consequences of dumping refrigerants. Anyway, scientists have tinkered with the concept of magnetic refrigeration for decades. The reason why magnetocalorics is suddenly attracting attention, however, is partly due to recent prototypes that research teams claim have achieved parity with existing vapor compression models. How is this possible? Lucky for us, this process can also be broken down into 4 steps, just like the vapor compression cycle. In fact, all forms of caloric cooling parallel the vapor compression cycle. A hypothetical HVAC based on caloric effects would, effectively, be substituting refrigerants for any material that, when manipulated, changes temperature. You start with a caloric material, which could be anything from rubber to ceramic, as opposed to a gaseous refrigerant. Then you apply caloric. That's because gadolinium is one blade in our magnetocaloric multi-tool. In other words, gadolinium is one of the most common materials that these devices can apply magnetic fields to. That's because gadolinium is one blade in our magnetocaloric multi-tool. In other words, gadolinium is one of the most common materials that these devices can apply magnetic fields to. In the presence of a magnetic field, gadolinium atoms align themselves in the same direction. This is called magnetic ordering, and it affects the material's entropy, basically, a measure of its disorder. When gadolinium enters this state, it actually heats up. Remove the magnetic field, and the atoms lose their alignment. The material enters a disordered state, its entropy increases, and it cools down. As this temperature change occurs, a heat transfer fluid like water can flow over the material to move the heat away, or bring it in, depending on the direction of the cycle. A single module would contain several of these solid caloric elements and a liquid that acts as the working fluid. By manipulating the material with magnetic fields and moving the fluid around with valves, you can maintain a stable cooling cycle. The effect isn't huge, but it's repeatable and reliable. And when you stack these modules and run them in a coordinated fashion, the results can be surprisingly powerful. Think of it as a magnetic heat sandwich. You layer magnetocaloric material and fluid channels between thermal diodes that regulate the flow of heat. The magnetic field is cycled in tandem with the switching of the diodes. And yes, thermal diodes are a thing. I wasn't making that up. At this point, you might be wondering, why go through all this trouble? Why not just keep using our tried and true vapor compression systems and keep filling them with new generations of refrigerants? Well, as it turns out, refrigerants are the real Achilles heel of vapor compression cooling. That's where things start to break down. Over the past couple decades, HFCs and other synthetic refrigerants have become the dominant option due to their chemical stability and performance, but not without environmental trade-offs. While HFCs don't deplete the ozone layer like the CFCs of yesteryear, they're still potent greenhouse gases, trapping thousands of times more heat in the atmosphere than carbon dioxide. That's one reason why governments are phasing them out. In the United States, the EPA is in the middle of a 15-year phase-down of HFCs. The European Union and Canada are also working on similar timelines. So, magnetocalorics, despite the complicated name, offer a cooling solution that's far simpler from a climate standpoint. There are no synthetic chemicals involved, and the working fluid is often water. Just water. Okay, but what about efficiency? Is magnetic refrigeration more energy efficient than vapor compression? Well, yes and no. The theoretical efficiency of a magnetocaloric system can exceed that of vapor compression, especially at smaller scales. This means things like beverage coolers, wine fridges, and even vehicle HVACs could see meaningful performance gains. One study in applied thermal engineering found that for refrigerators, magnetocaloric systems could achieve 20 to 30% higher efficiency than traditional compressor-based systems. But the tech is still emerging, and performance can vary depending on the specific setup. Scaling up is tricky. You need precise control of the magnetic fields, a fast and efficient method of cycling those fields, and robust thermal diodes or fluid valves. Fortunately, engineers have been hard at work refining the necessary components. In late 2023, researchers from Ames National Laboratory announced the development of a new type of off-the-shelf magnetocaloric material made from a combination of iron, silicon, and phosphorus. This new compound doesn't just reduce the reliance on rare earth elements like gadolinium, It also claims to offer a wider operating range with tunable properties. That means more versatility in the types of cooling applications and potentially lower production costs. If these materials can be mass-produced efficiently, they may pave the way for affordable magnetic cooling systems in consumer appliances. Still, magnets aren't the only game in town when it comes to caloric cooling. As we covered in our elastocaloric video, there's a whole family of materials and systems being explored for solid-state cooling. Barocaloric, electrocaloric, and elastocaloric systems all use different kinds of stimuli to achieve phase changes and temperature shifts. Each approach has its own pros and cons. But magnetocalorics are one of the more mature and studied options, which is why they're leading the charge, at least for now. To sum it up, magnetic refrigeration has the potential to revolutionize the way we cool our homes, our food, and even our cars. It's cleaner, potentially more efficient, and avoids the environmental risks of synthetic refrigerants. The core concept is simple: no moving gases, just solids and magnetic fields doing their thing. The challenge lies in engineering robust, cost-effective systems that can scale beyond lab prototypes. As materials science continues to advance and climate regulations tighten, we may see more magnetocaloric devices entering the market. And who knows, the next time you grab a cold drink on a hot day, you might just have magnets to thank. So what do you think? Would you be willing to replace your current fridge or AC with a magnet-based one? Are there other cooling technologies you're curious about? Drop your thoughts below and share this video with someone who still thinks magnets are just for holding up shopping lists. If you liked this video, be sure to check out my previous deep dive on elastocaloric cooling. Be sure to subscribe and hit the bell if you think cool tech deserves a warm welcome. Thanks so much for watching, and I'll see you in the next one.